Hi. Hi.
Can you hear me like that? Okay. I'm Alexey from ETH Zurich, and today I'm going to present you our work about GPU programming with contracts. So these days, we have more than one option for choosing a computational device. Traditionally, most of the computations were done on CPUs, which are quite sophisticated devices these days. So we have a very complex structure inside. We have multi-layer caches, lots of optimizations, and multiple cores. Multiple, typically, it's like 10 in tens or like several, not hundreds. On the other hand, we have GPUs that turned out to be pretty efficient computing devices as well, featuring hundreds or even thousands of cores. The difference is that each of these cores is much simpler than a corresponding CPU core. So if you want to leverage this computational power, you have to adapt. Typically, during discussions, these terms are used. So everything that's happening on the CPU side is called host. Everything that's happening on GPU side is called device. So device data, device computation, stuff like that. So the problem is that if you want to even approach GPU computing, you have to use very specialized API. So there are two main languages out there. It's OpenCL that can be used not only for GPU computing, but for any accelerated computing, and CUDA that works for only NVIDIA cards. And there's Microsoft AMP if you're a Microsoft fan. So in our work, we focus on CUDA because we happen to have a GeForce card. But the concepts are API independent. So if you want to develop a CUDA program, that's how your structure of your program looks like. So you have two disjoint things. You have source code for host code that is usually written in C, C++, and you have traditional compilation of that code. Use traditional C, C++ compiler, traditional linker. And device code is written in sort of C-like language, which is typically pretty restricted, so you don't have a lot of essential features. Most of the time, you don't even have recursion, for example. And you have to use different source code, different tool chains, until you generate objects files, and you can finally link them together into a single executable. So that's a very simplified workflow, how you could develop a program that runs on your graphical cards and maybe provides you massive speed up. So on the host side, you have to input your data somehow. You have to copy the data to GPU. You have to set up your device. You have to wait for completion, and you have to copy data back to main memory. And on device, you have to do only one thing, that is write the code that solves your problem. This code is often called kernel. Well, the problem is that writing a kernel is not an easy task. And if you're not very familiar with GPU programming and low-level C programming, it may be a very difficult task. So this is an example of a simple program that does vector addition. So it accepts a vector pointer to accepts two vectors A and B and outputs vector C, and that's not very intuitive. What's worse, you don't even have traditional imperative or object-oriented programming constructs like loops. So here you have to reason in terms of blocks and threads on device, which is pretty low level, and you don't have a loop. You have a branch that you're inside the borders, then you update corresponding value. So this is not very productive, and we want to try and provide some better API for a programmer to, so that it's similar to the language programmer is using, and at the same time is efficient in the sense that it's comparable to implementation written in plain CUDA. Well, actually, that was just some basics that you have to know if you want to even start. So what about other languages? What if you want to program in a language different from C? I must tell that it's a very active research field, and new approaches and frameworks appear pretty much every week. But we'll focus here on one of the simplest options, that is, kernels are still written in C language, like CUDA, and a special library called binding is required that communicates with the C level. There's a bunch of such libraries for popular languages, for Java, for .NET, for Python. And as we like to work with contracts, we're using IFIL, which supports contracts natively as a part of the language. And as it turns out, there's nothing for IFIL out there. So we propose our own solution called SafeGPU. So what SafeGPU is all about? It's a framework that is library-based. It is modular in the sense that a programmer can compose smaller pieces into bigger ones to solve harder problems. It supports contracts natively, and it tries to completely encapsulate GPU internals from a programmer, so it is accessible to a wide range of programmers. And it's built on top of basic CUDA integration, which is just simple binding. So this is sort of component diagram. So when a programmer uses SafeGPU, what he sees is only IFIL and SafeGPU API. So we keep look and feel of traditional IFIL. And SafeGPU communicates with C parts, SafeGPU externals, which are all the same for every program, and CUDA program that is relevant and was generated by SafeGPU for the specific problem. And then it calls compiler and VCC, and then we generate intermediate files that can be loaded in the program, but programmer doesn't see all that. He only sees the interface of IFIL and SafeGPU API. So that's the very basic thing that SafeGPU does. It translates code like on the left side. So this is code for vector addition into code on the right side, which is maybe not so intuitive. And the thing is that code that sums all elements of the vector, for example, which is pretty simple thing to do in traditional programming languages. It turns out it's 30+ lines of CUDA code only for that part, without any setup. So we hide all that complexity, and programmer only communicates with the left part. So SafeGPU API is based on collections. So we provide support for 3 types of collections. First is called collection. It's just a container of some items. We don't have any restrictions on these items. And so what the programmer can do with that, we provide functional API that allows to modify these collections. Also have support for bread and butter of GPU computing. It's vector and matrix math, all like matrix multiplication, matrix vector multiplication, all the things you can expect from classroom GPU example, and much more. So the API is vector-based, so you don't usually operate on individual items, but rather you perform operation on the collection, the whole thing. So here's some of the collection methods. Not everything here is important for this presentation. I'd like to mention a couple of methods. So what you can do with collection, you can produce another collection from a given collection with the help of the following methods. For example, you can filter items that satisfy to a given predicate. Predicates, it's like a high-level concept. It's just a pointer to a function in C terms. In IFIL, these guys are called agents. It represents a function that accepts an item of type T and returns Boolean. So filter will return all the items that satisfy a given condition. So also you can apply arbitrary transformation to every item of the collection. You can do queries that tell you if some property holds for every item, for some items. You can apply arbitrary action to a collection, and so on and so forth. You can also access individual items if you like to, but that's not the way you are encouraged to do. And there's one special method called update that is used with, you don't usually call it, but sometimes it's useful, and I will explain why in a moment. So with all that said, this is a complete example for quicksort written in SafeGPU. The core part of that is when we divide the unsorted collection into 3 parts. So if we filter it, form left part, all the items that are less than pivot, and we choose pivot to be the middle of the collection. And then we have middle part that's equal to the collection, and right part that is greater than the collection. And then we apply it recursively on the left part, and we concatenate it with the middle, and we again concatenate it with the right part. Also know that there are some contracts that is precondition. That's the condition that a caller should satisfy, and some post conditions. That's our guarantees to a caller that what will hold true after the call to this function. And that's all written in SafeGPU, but it looks and feels like I felt, because in the end we hide the backend of these guys. You don't know where it's performing. So as I said, SafeGPU is modular in the sense that you can combine several low-level operations into high-level one. And we defer execution because of that. You don't want to... For an example, when you compute in a square of equal distance, you have to do 3 low-level actions. You want difference between vectors. You want to have a square of each element, and then you want to sum it up. So you don't want to go to a GPU side back and forward 3 times to perform each of the simple actions. Instead, you want one composite action that has only one round trip, and we can do that by deferring the execution. So when SafeGPU encounters something like that, it doesn't immediately calls that. It rather defers it until the very moment when a programmer needs it. And programmer needs it either when it is calling a scalar instruction like sum, which returns a single value, or by calling a special method update. You can force deferred execution like that. And when we have deferred execution, when we can do workflow optimization. So there's optimizer that's looking for some patterns in the dependency graph that we construct. And I want to mention 2 main patterns that we have. First one is reduction merge. It is encountered in this simple example. When you want to compute dot product, first you multiply 2 vectors component-wise, and then you perform a sum. So dependency graph for that looks like that. So circles are data, squares are computation, and that's the dependency graph before the optimization. So you have to do 2 squares of computation. And after optimization, when we merge these 2 things together, you have only one computation. And on a GPU side, it's divided by a barrier. But as a programmer, as a SafeGPU programmer, you don't have to worry about that, about the synchronization. We're doing it for you. Another optimization pattern that we're heavily using is vectorization. So assume you have some vector math. So we compute some vector expression, and on 2 vectors A and B, and you multiply it by scalar. So that's the dependency graph before the optimization. So you need to multiply by scalars, then you have to sum it up. Again, there's 2 computation squares. After optimization, we can merge it into one complex computation that just has this complex action on single item. Potentially, we're changing number of inputs on GPU side, on device side, but again, it's all hidden. And by applying these patterns before the execution, we do the workflow optimization. So how do we evaluate that what we've done is actually useful? So we selected, we designed a benchmark set, small benchmark set, consisting of 6 problems. Out of these problems, some are very well suited for GPU computation, such as vector addition or matrix-matrix multiplication. Some, such as quicksort, and to a certain extent Gaussian elimination, are not so because they have recursion. You can do it recursively, but they also need access to individual items, so you have to select pivots, you have some complex logic, so it's not very straightforward. Can't do it very easily on GPU side. And on these 6 problems, we measured 3 factors. Raw performance, meaning that we compare the performance of our solution, sequential IFIL, and plain CUDA. Then we measured code conciseness, just code size. And then we measured contract overhead. So the last one is the most, it's a bit tricky to explain, so I'll go in details later. First, let's take a look at performance. These are performance graphs. On a vertical axis, it's time in logarithmic scale, so the less is better. So red color is sequential IFIL, blue color is plain CUDA, and green color is SafeGPU. So this is some interesting plots. What we can assume? Well, that SafeGPU is, or just GPU computing is not always the option to go. If your problem is small, then the sequential codes will outperform you on it will outperform you. But as soon as your problem scale goes up, or you have more difficult problems, then GPUs start to outperform CPU computing. So that's first observation. Second observation is that for most of the problems, SafeGPU is on par with CUDA, except for Gaussian elimination, where it's lags behind. It's getting slower. That's because we combine loops and GPUs, so we call kernels in a loop, and that actually gives some performance disadvantage compared to the implementation with just CUDA. So overall, it's pretty on par. It behaves no worse than CUDA for most of the examples. Is it better than sequential computing? It depends on your problem size and your problem complexity. So for matrix multiplications, it's almost always better to use GPUs. For vector addition, yeah, it depends. I will not show code conciseness because this is a pretty simple metric, and it's better to discuss contract overhead, which is the most interesting part, I think. So the problem with contracts that they're great for debugging, but in finalized mode, they diminish program performance. And actually, so they're usually turned off. They're still useful as they report improve debugging, and they can catch unexpected errors even in production. That's what we want to keep. So the question is, can we use massively parallel GPUs to try to solve this problem? And can we keep the contracts in finalized programs? So how we set up our experiment? We measure the overhead of the program with contracts in finalized mode compared to the performance of this program without contracts in one of the following presets. So we keep all contracts, that is preconditions, postconditions, invariants. Then we only keep preconditions and postconditions, and we only keep preconditions. Why we do this? Why we do this in 3 modes? Well, because invariants are really heavy, and you can easily get a performance advantage by turning them off. And then post conditions, it's like you guarantees to your caller, and most of the times you're not interested in that. So the most practical setup is when you keep only preconditions. That's like in programming without contracts is just checking your arguments. That's you should do, and the contracts are doing that. And then we compare the overheads for IFIL and SafeGPU programs with equivalent contracts. And also another important thing, we distinguish between two types of contracts. We don't care where they appear, but we care about how they're evaluated. There are scalar contracts. Their computation time doesn't depend on the collection size. So for example, that your vector is not empty. You have to only check one variable to do that. You don't care how many items in the vector you have. Then we have range contracts. The evaluation time usually linearly grows with the collection size. So one example of that is checking if vector is sorted. The more items you have in the vector, the more time it takes for you to check. The intuition is that keeping range contracts in the finite version should be very negative for performance because you have to do more and more work. So now I will present you a set of benchmarks that with these overheads. First, we go take a look at programs with scalar contracts. Then we take a look at programs with range contracts, and we'll see the overhead. And I will not show you the modes with preconditions and postconditions. I will only show you this mode and this mode. So this is preconditions only. So orange bars are SafeGPU overhead, green bars are IFIL. So the closer to one, the better. And this scalar contracts with only preconditions. As you can see, SafeGPU scales pretty well on these problems, and IFIL is performing reasonably well on first two, on small sizes, and then the overhead is really huge. And so if we turn on full contracts, preconditions, postconditions, and invariants, things for IFIL get even worse. The overhead scales even more, and SafeGPU is still fine. So for range contracts, the situation is kind of the same. So if we keep only preconditions, IFIL also starts pretty high in terms of overhead, and SafeGPU doesn't care. So there is some overhead towards the end. So when you have big problems, then SafeGPU has like 10% of overhead. And this still true when you have full contracts with range contracts. And for example, for matrix transposition, IFIL is almost unusable because you have like 10 times overhead with contracts. So that's not feasible. So what can we conclude from these benchmarking results? Well, if you have only preconditions, it helps with the performance of the traditional contracts. I didn't show you pre and post mode because it doesn't really matter if you have all contracts checked or pre and post. That doesn't make any significant difference. So if you have traditional program and keep contracts, you have at least 2 times overhead. And it gets worse when you have preconditions and invariants. And contracts in SafeGPU occur little to no overhead in every setup. And surprisingly, presence of range contracts has little impact on slowdown across all these problems. So there's still some ongoing work on this project. So first, we want to extend this evaluation with different contract provider, for example, C# and CUDA contracts, to reach a little bit different community and maybe have more interesting benchmarking results. So we have to add better support for custom classes. That's not primitives. Of course, adding more optimizations to optimizer is always an option. It would be interesting to provide more collection types, for example, associative arrays or maps. And we want to investigate how we can integrate SafeGPU approach to task parallel models because we want to have advantage of both models. Okay, so conclusion, I present you SafeGPU. That's library-based framework. It's efficient, at least as efficient as CUDA implementation. It's modular, and it's equipped with contracts. Thank you. What do you mean optimizations? So okay, I get it. So for most of the problems, we took the implementation of these problems from examples from shipped with CUDA programming toolkit. So we didn't do this implementation ourselves, so we took what NVIDIA tells us is a good implementation.
What's the most complex contract?
Complex in what sense?
Computation. So if we're comparing that sizes of, say, two vectors were equal, did you ever have to look at actual matrix properties?
So, for example, from matrix composition, we check that the result is actually transpose matrix. So it's yeah. But mostly we are focusing on linear contracts.
So for the contracts on the using SafeGPU, I guess there's a overhead in that has to use extra cores to check the contract, right?
Yes.
So there's not a speed overhead, but a space overhead one.
So you're saying that SafeGPU has its own contracts, right? Is that so? What is the question?
The question is how much more computational power do you need for the contracts on using SafeGPU?
Okay, so if it's color contracts, we don't need any extra computational power because we check it on CPU side. If it's range contracts, at least that's what we tried, it usually takes linear time, linear over the size of elements. And if the problem is not linear, say you have something with matrices, then yeah, you have like a little bit of extra computation time linear, but your algorithm is quadratic or cubic. So it's not very noticeable. So the most overhead we could get with SafeGPU is 13% over the version without contract. So we use SafeGPU, of course, to execute these contracts. So use the API provided by SafeGPU to write these contracts. Either you call embedded methods like assorted, or you can use this filtering function API to form your own contract.